Okay, so the last thing that we talked about was if you have a transformation in the format of a matrix vector multiplication to produce an output vector like this, or if you may also equivalently have a subband decomposition in the form like this with some filters H0 and H1, which will correspond to subband filtering, which has its fundamental roots inheriting from wavelet theory. So these H0 and H1 and their corresponding reconstruction filters, G0 and G1, they will be named, and their design is an issue that must be handled very carefully. But let me tell you, or let me show you how reconstruction of one band is done. It is quite simply this to be H0 and downsampling, and H1 and downsampling. These must be encoded. If they are kept the same, then the reconstruction filter is first done by upsampling filter, and then the proper synthesis or reconstruction filters G0 and G1 must be designed, and they pass through those filters and they are added to produce, let's say the input is X of n and the output will be Y of n. So with a proper design, and if nothing happens in between, X of n will be exactly equal to Y of n. But we know from our previous discussion that if the transformation, if the matrix transform, for example, is an orthogonal or orthonormal transform, then the amount of error that you make in between will exactly reflect to the amount of error that accumulates in Y of n. For example, if the coefficients here, let's say there are 4 coefficients, they are 10, 9, 8, and 1, okay? If these are the coefficients. And if you just chop off this small one, just for compression purposes, so that it's a 4-to-3 compression. So you drop this 1 and you retain only these 3 coefficients. So what was the value of this 1 that you dropped? It was 1. After the reconstruction, the amount of square error is 1 square, which is also 1, by the way. So the error that you do here reflects to the error that you reconstruct after the inverse transformation. But that's valid, as I say, only for the orthonormal transforms. There are a class of H0, H1, and corresponding G0, G1, which are also orthonormal, and therefore they will be, we will have the same kind of situation. If you make some error here or here, the same error reflects to the overall accumulation. That helps a lot in evaluating or making comparisons of the compression performance of transformations. Even if H0 and H1 may not cause an orthonormal transformation in these branches, or even if your matrix multiplication is not really making corresponding to an orthonormal transform, actually you can still make some quantization errors, some chopping of business in between to the transform output. But then it will be difficult for you to guess what is happening at the reconstruction stage, because you have to now reconstruct after quantization or chopping off, and you have to see what kind of an error it makes experimentally. You have to make an evaluation. But for orthonormals, the transform output is sufficient to make an assessment. And at that point, if these transform outputs, let's say the transform outputs are Y1, Y2, up to Yn, it's an n-branch transformation. or a matrix corresponding to capital N by capital N that transforms x1 up to xn into these transform coefficients. If the square values, the energies of these branches have a tendency to decrease like this. So this is the magnitude, and this is the index, as you see. Then that is a kind of transformation that we use a lot for compression purposes. It's like pushing most of the energy into some few coefficients around y1, y2, maybe y3, etc. And some other coefficients, transform output coefficients, have small energies. And when I get rid of them, if I quantize them badly, then I will not make a lot of error because their square magnitudes are, as you see, very small. And if you get rid of them, you make that much error, which is not much, which is not a lot. That is known as the phenomenon of making that kind of a comparison is known as looking at the so-called basis restrictions, and therefore it is the basis restriction error that we will mostly compare about the compression performances of the transforms. But for orthonormal transforms, of course. You can, of course, still look at the basis restriction error for non-orthonormal transforms, but then you have to reconstruct first and then look at the error. So the error monitoring will be a little bit difficult. In general, we know from information theory that if you reduce the rate or increase the rate, and if you monitor the distortion, then what we get is so-called a rate distortion curve, which is like an inverse proportion within one another. One of them is inversely related to the other one. If rate is small, distortion is large. If rate is large, distortion is small. So if you have a finite transformation, not a streaming transformation like a subband decomposition, but let's say a 16 by 16 matrix transformation, it usually looks something like this. So it never goes to negative. Sorry if it looks that way. Suppose that this is the n by n matrix's last index, n. So the rate, it's a full rate. It means you are using all the transform coefficients without dropping any of them. Then you see the distortion is 0. But if you reduce the rate from n to n-1 to n-2, n-3, etc., it starts causing some distortion because we are getting rid of some of the transform outputs, and we are not using them in the inverse transformation. We are just chopping them off and replacing them with 0. So the distortion increases, and it increases to a maximum level also equal to the signal energy, because if you reduce the rate to 0, it means you're losing all of the signal, and the distortion is equal to the whole energy of the signal. So this kind of a curve is known as the rate distortion curve. You may compare the performance of your specific transformation by fitting or by drawing the rate distortion curve, experimental rate distortion curve, or some statistical input. You may generate some statistical input like an autoregressive AR1 sequence, for example, with rho is equal to 0.95. You may just experimentally generate that. And then you make experiments, you make tests of reducing the output, which means restricting the number of bases that you're using. And the more you restrict, the higher distortion you get. And you compare it to another transformation. Suppose you have DCT and you're claiming that your transform is better than the discrete cosine transform for these kinds of statistical inputs. So in that statistical test signal range, you repeat the experiments and you make an average of these rate distortion curves and then draw them side by side. Suppose this black one is the discrete cosine transform and this is your transform. So this is your transform. And the other one is, let's say, DCT. Now, if you come up with this kind of an output, and if you're writing a paper and if you draw it like this, what kind of a result does it correspond to? Is your transformation better than DCT for this experimental set, or is it worse than DCT? Any suggestions from your side? I'm listening to Sabri or Abdul Majid. No comments? Which one is better, the DCT or your transform here? Couldn't hear.
I think DCT.
Yeah, this DCT seemingly from this shape is indeed better. The reason is that, for instance, at the same point of a rate, at this rate, for example, let's call that it's M. DCT makes this much distortion, but your transform makes this much distortion. And as you see, your distortion is larger than the DCT distortion, therefore your transformation is worse. And in general, as I can see from this figure, it's worse from DCT, worse than DCT everywhere for all rates. For example, sometimes towards the right-hand side, it may be better, yours may be better, and you say that at high bit rates, I perform well. I perform better than DCT, but for lower bit rates, DCT outperforms my transformation. That may happen, but it doesn't happen here. It's seemingly your transformation is inferior to DCT everywhere. So you compare it to DCT like this. It's always a good idea to always compare to KLT. So always compare to KLT, which is the statistically optimal transformation. It's very difficult to have a case where you construct KLT from the test images and then you compare your results with the test images too, and you see that you may you may have a better performance than KLT. It's very unlikely. It's almost impossible to beat DCT on the average of the statistical case. But the nearer you approach to the KLT curve, the better transformation it means. So if your transformation is better than DCT and more closer to KLT, then you can say that I come up with a very good transformation. So that's also a good way to make a comparison. But now I will, at this point, talk about another style of bit allocation instead of cropping or chopping off the transform outputs completely. So I will be talking about optimal bit allocation. So what do we mean by that? If you remember what we did for Jpeg, you may notice that we were dividing by some numbers and then rounding off or truncating to an integer. It's a vague means of assigning bits to these 64 coefficients. But actually, there is also a methodological way of assigning bits. So how many bits can I assign to an output of, let's say again, y1, y2, up to yn. So I have n channels. To be compatible with my nodes, I'm gonna make this ym. So I have m channels at the output. It may be subband decomposition, it may be a matrix transformation, and the outputs are y1 to ym. And I have a total of, or an average of rk, or let me not say rk, but an average of r bits per sample. But that sample is not really evaluated within itself. I will make chunks of these outputs, and for the total chunk, this means that I have a total of m times r bits that I will distribute among these y1 through ym. So on the average, for each of those, I have r bits, and I have a total of m times r bits for these. If I don't make the transformation, therefore, I will be having x1, x2, up to xm. And for each of them, I will use r bits for the first, r bits for the second, and finally r bits for the last. So a total is m times r bits. And I will that will correspond to some distortion, because I'm not using real numbers now, although the input signals were real numbers. I will be like quantizing them, applying a quantization of 2 to the r levels using r bits for each of them. This is called, by the way, PCM, pulse code modulation. It means quantization without transforms, and that is uniform quantization without transform. For example, if you are listening to CD audio, it makes 16-bit quantization to each sample that is sampled at 44.1 kilohertz. Okay, that's the sampling rate, and for each sample, 16 bits are used. So 2 to the 16 levels are applied, and it makes a distortion, because originally, as we know, the analog audio signal had continuous values coming from the microphone, from the recording scheme. But as soon as we convert it into digital, now it has some levels, it is quantized. But the comparison or the strategy that we will use is as follows. Instead of assigning r bits to each of them, is there a better way to make an assignment in such a way that to the first y1, I will use r1 bits, to r2, to y2, I will use r2 bits, and the final value ym, I will use rm bits. And this total will still be equal to m times r. So I'm not really reducing the bit rate. It's not like compression, but it's like encoding for higher fidelity or lower distortion. So in the end, the amount of error that I will do here will be more than the amount of error that I do here. So I will reduce the distortion by making the transformation from x1 to xm to y1 to ym. Okay, so I will compare them at the equal rate. So it essentially looks like this. I'm assigning a bit rate here, m, and at this bit rate, after the transformation, will it be lower? Will it correspond to a lower distortion than the PCM distortion. By the way, the PCM distortion is essentially, let's draw it in green, for example, like this. It will be a straight line. So this is PCM. If you don't really do any transformation, that's what you get. So you are trying to pull it downwards. Okay. Okay. Now, what is the amount of error at each branch of the transformation? With or without transformation, it will be like this. It will correspond to the variance that we're talking about. So at the kth branch, the variance, which means the error, is equal to a constant times 2 to the minus 2 RK, the amount of bits assigned to the kth channel, times the variance of that channel. This sigma theta k square corresponds to the variance of the channel. So you make that much a distortion. And you can actually see that this is a valid formula from the previous week's lectures, because at some point you must remember that we obtained a distortion of a uniform quantization to be equal to delta square over 12. You remember that? That was the uniform distribution, uniform quantization error. We discussed about this during the discussion about quantization. And when you make, when you look at it from a different perspective, it's also equal to 1 over 12 times 2 to the minus 2 times R, where R corresponds to the amount of bits that makes delta square, or that corresponds to delta in the quantization interval, because as you see, this interval is split into quantization intervals, and each of that is delta, which is equal to 2 to the minus R, right? And because it is normalized, first of all, and therefore delta square over 2 here will correspond, delta square over 12, excuse me, corresponds to 1 over 12 times 2 to the minus 2R. So you see 2 to the minus 2R is here, and it's reasonable to have it here. And this 1 over 12 is alpha, by the way. And times 1 is the variance of the channel, which corresponds to a uniform distribution of a range of 1. Therefore, this sigma theta k square is taken as 1. But that was just an example. I'm showing you this for you to understand that this is indeed the reasonable distortion for the channel, distortion expression for the channel. And since one of them is sigma RK square, the total error, this is the total, is equal to the summation from 1 to capital M for all branches, in other words, alpha k 2 to the minus 2 RK sigma theta k square. So now, how can we allocate RKs in an optimal way? By the way, I will presume that this alpha k is like always 1 over 12 or something like that. So it doesn't really change, because I will be using the same methodology for using the quantization bits for each channel in an equal manner. So alpha k could be taken out of the summation as alpha, for example. And but these variances, of course, will be different. Therefore, RKs will be different. So how can I minimize this total distortion? And from KLT, you may start understanding or learning the fact that the trick here is always to take the derivative with respect to the optimization parameter and equate to 0. So take the derivative and equate to 0 for optimization. So we will generate a figure to be optimized. Let's call it J for the in overall term, because it's not only sigma r squared to be taken the derivative and equating to 0, because when you do that, it will give you these rk's to be equal to infinity. So by assigning infinitely many bits to every branch, it will give you the smallest, the minimum error, of course, right? That's obvious. If you have infinitely many bits, it will correspond to the minimum error. It will correspond to no error, actually. But that is only the part of the truth, because we have another constraint. The other constraint is we have a total of m times r bits. So you cannot say rk is equal to infinity, because otherwise their summation will be infinity. Their summation will not be equal to m times r. So we have to take into that account and make it a constraint. So the total thing will be a constrained optimization, like alpha times k from 1 to m. So I'm writing the sigma r square. So alpha was already taken out of the summation. 2 to the minus 2rk sigma theta k square. So this much is the one that we are trying to minimize. And the condition, the constraint is a Lagrange, within a Lagrange multiplier, like r minus 1 over m k from 1 to m rk. So this last term here makes sure that this summation is equal to r times m, and these rk's will not overshoot to go beyond that. Otherwise, with this minus and this second minus, it will be a plus, and this term will tend to grow indefinitely, but we are minimizing it. Therefore, we are suppressing this term not to go to infinity beyond the range where this summation is equal to r times m, as you see here. So that's the constraint, imposition of the constraint. And from there, now we can take the derivative of J with respect to what? The thing that we are gauging, we are trying to adjust, are essentially RKs. So what? How many bits should I allocate to the kth channel? So for different k values, we will have to take the derivative with respect to rk and equate to 0. And it's going to give me an rk value, because this thing is in terms of rk. We have it here, we have it here, and therefore we need to take the derivatives and then equate to 0, the derivative to be equal to 0, and solve for rk's from this equation, which is a cumbersome operation, and I'm not going to do that. So that's bad news and good news altogether. But it is good news, because I will tell you what the result will give. It will give you this. This logarithm base 2, you may ask to yourselves, how can we come up with a term of logarithm? The reason is that it's in the exponent already. So in order to solve for it, we have to take the logarithm of both sides of the equation, etc. It's a cumbersome operation. That's why it's a cumbersome operation. But it's here anyway. 2 alpha ln 2 sigma theta k square minus 1 over 2 log base 2 of lambda. So the solution actually does not look well enough. It's not like a solution, really, because we still have lambda to be determined. What is lambda? So that we substitute back what is lambda into this equation furthermore to eventually find the correct expression of Rk. So how can we do that? We do it like this. Substitute m times r is equal to summation k from 1 to m Rk into here, into this equation, and we solve for what is lambda, and it happens to be this. It is the multiplication. You may remember this symbol. It corresponds to the multiplication, running multiplication, like the sigma, capital sigma corresponding to the summation. So this is multiplication of from 1 to capital M to alpha ln 2 sigma theta k square mth root 2 to the power 1 over capital M times oh sorry, it's not r, it is 2 to the minus 2r, where r is the average bit rate. So you find lambda like this, and you have to now substitute this lambda back into the expression. So we substitute back into this expression, and then we find finally Rk to be equal to this. This is an awesome result, and understanding this result makes more sense than trying to derive it mathematically. So it is R, which was the average bit rate, remember that, plus 1 over 2 logarithm base 2. This base 2 looks ugly, sorry, let's write it like this, of sigma theta k square divided by multiplication from 1 to m, sigma theta k square to the power 1 over m. So to the power 1 over m means mth root. And when you look at this denominator inside the logarithm, it is also known as the geometric mean. It's not the arithmetic mean, but the geometric mean, which is like multiplication of the items and then taking the mth root of that. If, for example, you have two elements, k is equal to 1 and 2, for example, you multiply sigma 1 square and sigma 2 square, and then take the square root of it. So you find the geometric mean of sigma 1 square and sigma 2 square. So that the thing that we have here is the geometric mean of the channel variances. Always keep in your mind that after the transformation, we have these channels of y1, y2, y3, y4 up to ym, and they have their corresponding variances, the energies, in other words, all the way down to sigma theta m square. So these are the energies. And here, this denominator is taking the geometric mean of these. At the top, it's the corresponding energy of the channel. For example, at the second channel, that is sigma theta 2 square in the numerator, divided by the geometric mean. Now, the total or the average of these cannot change because this is an orthonormal transformation, which means that the average of the sigma theta 1 square, the arithmetic average of this all the way down here is essentially the same as the signal energy, because it's an energy preserving transformation. But the input energy is uniformly distributed, and after the transform, the energy distribution changes. Sigma theta 1 square is larger, a lot larger. Sigma theta 2 square is smaller, the next is smaller, etc. And it gets smaller and smaller all the way down to here. But the averages will not change because of the orthonormal transformation attitude. The total energy doesn't change, therefore the average energy does not change either. But some of them will become smaller. If something becomes smaller, then the geometric mean tends to become smaller. What do I mean by that? For example, suppose that you have two items which are 6 and 6. What is the geometric mean of that? So the mean geometric of this is 6 times 6 square root, which is equal to 6. Now, I want to keep the arithmetic mean the same. The arithmetic mean is 6, of course. So the two items I will change a little bit, like 3 more of one of them and 3 less of the other one, like 9 and 3. Okay. So the mean is again 6, but what about the geometric mean? It's equal to 9 times 3 in square root, which is square root of 27. And it is significantly less than, it's of course, less than 6. So as you see, as the balance changes, this geometric mean becomes larger. So that's what makes this denominator to be a larger number. And it becomes even worse if you, for example, say that it is 11 and 1. Again, their average is 6, but their geometric mean is square root of 11 times 1, which is square root of 11. Of course, it is less than 6. It is even much more less than 6. So the situation of improving this denominator is a tricky thing, okay? And you can only achieve it by making these energies as unbalanced as possible. So you want to make some of them quite small. If you can make them 0, actually, things start becoming too interesting, and the denominator essentially becomes a 0. And if you divide anything by 0, it makes infinity, etc. So some nasty things start happening over there. We will take a look at how much gain we make by making these as unbalanced as possible. But before that, let's look at what this really means. First of all, there is an R, so there is a base R here. And you add something. That additional something can be sometimes positive and sometimes negative. If it is positive, it means you are assigning more bits to that kth channel. If for that kth channel this happens to be negative, it means R minus that, so you assign less bits. So which channels do you assign more bits? Which channel do you assign less? It depends on this ratio. If your variance is above the geometric mean, then this ratio is greater than 1. And since it is greater than 1, the logarithm of it is positive. So you add on to R. However, if your variance is, if your channel variance, channel energy is less than the geometric mean below it, then this ratio becomes less than 1 and the logarithm becomes negative. So you subtract something from R. So that is how you make the assignment, by looking at this ratio. And clearly, for some of the branches, sometimes the channel energy will be above the geometric mean. For example, this channel, the first channel energy will usually be way above the geometric mean. So this thing will become greater than 1, and you therefore assign more bits to the first channel with large energy. Therefore you assign bits according to their energies. The higher energy it has, the more bits you assign to that, and the less energy it has, the less bits you assign to those. And you have to have a total bit budget. You have a finite amount of m times r bits, and you're making assignments to the channels. So this idea tends to assign more bits to higher energy channels with higher energy. This essentially is the idea that we use for audio coding of Mpeg audio layer 3, MP3, as we all know. We have a lot of branches, and some branches have higher energy, so we assign more bits to that to accurately make a representation of that channel. Meanwhile, the other channels will have less bits, so they will be coarsely quantized with higher distortion, but their energy is small anyway, so we don't really hear that quantization error. But overall, how can we evaluate the gain? For the gain, by the way, we have to compare everything to the PCM version of the error, where the PCM version is m times alpha times 2 to the minus 2 r times m times sigma x square. The reason that I didn't write it in a summation format, instead I just added up everything, all the coefficients, is that this sigma x square does not change in time. I'm assuming a stationary signal here. So from here to m further, I don't expect to change, I don't expect to observe any change in the variance or in the energy. So it's always the same. This alpha is always the same. So I have this kind of a result for the PCM. And the gain of transform coding, so this the name of this is transform coding gain, is the ratio of the quantization error using m times r bits for a chunk of m samples using PCM divided by doing the same to the transformation output. So this ratio will correspond to my gain, because I expect sigma PCM squared to be larger. So larger to smaller ratio will be a number larger than 1, which will be my gain, transform coding gain. And when we do that with the together with the cancellations, will give me this. Sigma x squared will be the only thing left in the numerator, because the others will cancel, the other terms will cancel with the terms corresponding to the denominator side. And I will be left with sigma x squared, just the variance of a sample, divided by the geometric mean of the channel variances. Now, you see the numerator does not really change. We cannot really increase it or decrease it. It is given, it's just the signal. Sigma x squared is evaluated and obtained from the signal. But the denominator, the geometric mean of the transform output can be altered, can be perturbed, or can be designed. The way to do it is to make it as unbalanced as possible, as I previously gave you with the example here. So if I reduce the geometric mean, then the coding gain increases. And the only way to reduce the geometric mean is by making a good transformation so that it pushes most of the energy to some of the coefficients and reducing the energy of the remaining coefficients, making it as unbalanced as possible. That's what KLT is doing. That's what DCT is doing all the way anyway. So this is the transform coding gain that you can evaluate. And with this kind of a transform coding gain, you can just give it numerically, say that my transform coding gain is this for this given particular test set of data. you can evaluate it and give it as a number. That's also another alternative to giving this basis restriction error or the rate distortion curve, which is also a very nice way of showing the performance of your transformation. But instead of that, you can also give me the transform coding gain, the overall transform coding gain. By the way, I can further extend this formula and say that the numerator, which does not change, sigma x square, is actually the average of the transform output energies. But the average is an arithmetic average, not the geometric average, like this. So this numerator is equal to sigma x square, because we know that the total energy after the transform is equal to m times sigma x square, which is the total energy before the transformation, because it's an orthonormal transform that we are considering. The numerator, the denominator will be the same, of course, like this. So we can now interpret in a different way. It's like the arithmetic mean divided by the geometric mean of the channels, right? It's also, it could also be considered like this. And the only way to improve this, you cannot really change the arithmetic mean because it's equal to sigma x square, but you can reduce the geometric mean by making it as unbalanced as possible. So it's like arithmetic mean divided by geometric mean. And the only way to increase the coding gain is by reducing this, which is done by make channel energies unbalanced. Okay, this is how we literally find it, the coding gain. So this is the coding gain expression that I want to mention about, and it's one of the last things that we will talk about for this semester and for today. The coding gain of the Cardinal-Liouville transform is theoretically the largest, because it shows the highest unbalance in the denominators. Therefore, it reduces the denominator as much as possible statistically. So you cannot really, you're not expected to beat the Cardinal-Liouville transform, but you can be as close to that one as possible. Now, finally, I want to very quickly mention about the algorithm of bit allocation. Because we didn't talk about the algorithm, we talked about the formula for the bit allocation. The formula is given here. You have to assign this many bits. But it's cumbersome, right? Every time you're looking at the logarithm of this thing and divide by 2 and adding to r, and that is the bits that you have to assign to that channel, etc. So if I give you like, I don't know, 16 bits for these 4 channels, how are you going to distribute these 16 bits to these 4 channels? There is an easier way to do it. It's an approximate way, and you can only do it in an approximate manner because this value could be a non-integer number. For example, the optimal bit count for this channel is, let's say, 4.3. So how many bits are you gonna allocate to this channel? Are you gonna allocate 4 bits or 5 bits? It's 4.3 bits is the optimal. So, but of course, you have to assign some integer number of amount of bits. So this approximate distribution algorithm will help you to resolve it, and of course it will be approximate, but it is there's a faster way of doing this. And the algorithm, I will just try to explain. I'm not going to write it in the form of a stepwise program, but what we will do is we will sort the energies first of the channels. Okay, we will sort them out, and then we will pick the largest one and increase its bit allocation by 1. For example, this is R1 is assigned to R1 plus 1 at each step, at each iteration step. So in the beginning, when you make the first sorting, R1 is, and as well as R2 and all the others, are all equal to 0, of course, because you didn't really make any bit assignment. So you allocate 1 bit to the largest energy. And then you divide this one and assign it to be the new energy. You divide it by 2 and assign to be its new energy. So you reduce the energy by half. You assign 1 bit, you reduce its energy by half, because every bit is capable of explaining half of the data. So you already explained half of the data. So now you can reduce its energy. You can consider its energy to be reduced to half, because half of the energy is already explained with that extra 1 bit. And then make a resort. You sort it again. So now probably sigma theta 1 square will not be the largest, but something the previous one, like sigma theta 2 square, will be the largest. So what you do is you assign 1 more bit to that, to R2 this time. But by the way, you have to decrease the bit budget by 1. So bit budget minus equals 1. So you subtract. Let me write it like minus minus. Okay. You reduce the bit budget. You have a total bit number of bits, of course. You sort again. This time the second channel is the largest. So you assign 1 bit to the second channel, and you reduce the energy of the second channel by half. You make it half, and you also reduce the bit budget by 1, 2. So because now you have used 2 bits. Now let's assume that the first is again in the top. It was 1 before. You assign 1 more bit. So you assign now 2 bits to the first channel, and its energy is halved again. So it's now 1/4 of the previous or the initial energy. And you sort again. So, and you repeat it and repeat as long as bit budget is greater than or equal to 0. Because if the bit budget is 0, then you have to stop. You cannot assign any further bits. So you make assignments like this, sorting, and so you see that my meeting is approaching. So I will have to stop within a few minutes. You assign according to the energy, and every time you make an assignment, you reduce the energy to the half of it. This is a very commonly known or a very well-known bit allocation algorithm. Now, these bit allocations and the transform coding gains that we see here, or bit assignment formulas that we see here, etc., they are, of course, all for non-artistic way of making compression, if you just make a quantization. But compression is more like an art than science, unfortunately, because for many cases, we don't really come up with, we are not desperate enough to resort to these methodologies. We usually come up with some better ideas. We can take a look at some further correlations between the channels at this stage and the channels from the previous stage. If there is still some cross correlation, we can try to exploit those cross correlations. For example, in subband decomposition, like this here, people have discovered that if the item or a sample at the subband channel here is small, they call it a zero, but it means it's small. Then similarly, with the same zeroness, with the same smallness, here the same coordinates but twice wider will all be zeros, and here with 4 times wider will all be zeros. So we have some zero here, which will induce that it's probably all zeros here and zeros here locally. So why are we individually and distinctly encoding the zeros here and here and here? Because we know that one of them will correspond to the other one. So let's group them all together and say that it's a 0, 3. It's a 3 from 1 to 2 to 4, a binary tree kind of thing. So that idea is very much used in compression of images in 2-dimensional subband decomposition. And in the next week, I want to show some particular examples to those interesting compression standards. They essentially became some standards because you can find them on the internet, you can download them, you can test them for yourselves, and they truly outperform Jpeg. Jpeg itself is also quite an art of an image compression, but the subband decomposition actually performs better than Jpeg in terms of rate distortion comparisons and coding gains. You may think to yourselves and ask this question: why then are we not using them? It's not a very commonly used standard because we are still using Jpeg. The reason is Jpeg is easy and it's local, therefore it doesn't require a lot of memory. The other compression standards usually use all the data top to bottom everywhere and using replicas of the image, which requires a lot of memory. But in Jpeg, we split it into 8x8 blocks and locally make the application, which is very fast, because if you have multiple cores or if you have dedicated chips for an 8x8 discrete cosine transform, you can make it a parallel process and take the DCT of the whole image all at once, right? So Jpeg is easy and it's so a well-known standard that we cannot get rid of it, although some other methods essentially perform better than that. Okay, by the way, you might have heard about the relatively newer standard called Jpeg 2000, and Jpeg 2000 actually is an extension of Jpeg that uses subband decomposition. So if you can find save as options of images in the format of Jpeg 2000, actually it corresponds to saving using this compression technique of subband decomposition and 0 trees. Yeah, but it's not a very common standard. So using some further ideas and strategies, by making some arts, actually you can compress better. But those better compressions are usually not available for analytic comparisons. We cannot really come up with a term like a transform coding gain like this one. Okay, this is a solid analytical figure, and you can always show your result with this coding gain. And of course, in the classrooms, when we are teaching something, we like things that are available for mathematics, but the art stuff is not available for mathematics. The only thing that you can do to propose an art way of making compression is by giving us experimental results with throughout a lot of data. So you may use a lot of test images and say that actually, as you see, my compression scheme outperforms yours. For instance, you can maybe you're not able to give me the transform coding gain to be superior for your transform, but you can say that for biomedical images, for instance, my transformation experimentally gives better compression results than the other one, because here are the results. But I'm not able to explain it using any mathematical formulas like this. I can just say that that is what it is. We will, next week, we will see a brief review of those art methods, like it is what it is methods. And of course, they have their ideas. The motivations are clear, but mathematically, it's not quite possible to make sense of them or to make solid comparisons. All you can do is experimental comparisons. So right now, I'm stopping the course, and we will not meet at 11 o'clock or anything. We will be doing just one long hour of a course for today. Next week, we will continue, and it will be some short introduction in the next week as well. And afterwards, if the weeks are already depleted or exhausted, then we will wait until you will make your presentations of your projects. Meanwhile, I will submit the take-home examination for the final, and you will have a lot of time to solve for the take-home examination questions. Okay, so have you any questions now? I'm stopping the recording and I'm ending the meeting if you have no questions.
I have a question about about the presentation. What the date specifically?
The specific what?
Date to
Date.
do that.
Yeah, the date, it is specific, but I don't know that because I didn't check, but it is specific. The specific date is the Monday, the same class hours of the first, oh, sorry, the last final exam week. We have a final exam week, right? In fact, we have two final exam weeks. The second, the later final exam weeks, Monday at the class hour.
Yeah, it is the last half of June, I think.
Yeah. Something like that, maybe. I don't know. And until then, we will be doing nothing. You will be just working on the take-home exam questions, and you will be working on your project and finishing your project. You will be doing. Yeah.
Okay. Thanks. Have a good one.
Thank you. All right then. If no more questions, then I'm ending the meeting and ending the recording. So see you next week. Goodbye.
See you.
See you.